Hello everyone, my name is Thore Tiemann and I'm from the University of Lübeck in Germany. I'm presenting to you today our work Microarchitectural Security of Firecracker VMM for serverless cloud platforms. This is joint work with Zane, Weissman and Berk Sunar from the Worcester Polytechnic Institute in the United States and my supervisor Thomas Eisenbarth here in Lübeck. So what are we going to look at today? First, I'll give a short motivation of why we were doing this work I'm presenting today. Then I'll give you some background on micro VMs, meltdown, microarchitectural data sampling attacks, and Spectre attacks, just to fresh up your memory. And then we will have a look at the threat model that we're considering before we see what we found in our analysis of Firecracker in the context of MDS attacks and Spectre attacks, before we draw a conclusion and then finish the talk. So why did we do this? You've probably all heard that serverless computing is one of the emerging trends in cloud computing. And the nice thing about serverless computing is that you can execute short-lived functions in the cloud without having to process or care about hardware, operating system setup, or runtime management, right? Because you can rent the hardware, the operating system, and the runtime stack from your cloud service provider. You just upload your code and it will run automatically for you. And because those functions are very short-lived, hypervisors or cloud service providers will usually place multiple tenants on the same machine, because otherwise cores would idle, right? The CPU would not be used in its entirety. So cloud service providers usually place multiple tenants on the same machine to have them share resources, because one might use more memory and the other one might use more CPU time. And then this will average out so that the whole system is used at a good ratio. On the other hand, we have seen a lot of microarchitectural attacks in the last 5 years, I would say. And those microarchitectural attacks, they are inherent to the microarchitecture of a CPU. The problem with those attacks is that they ignore privilege boundaries and allow an attacker to extract information from a process or a tenant, right? It does not have to be a process. It could be a virtual machine or some higher privileged code, for example. And it could use those attacks to extract information across those protection boundaries. And the thing about microarchitectural attacks is that they require the attacker to share microarchitectural resources with its victim. And you may spot the problem here already, because several tenants per machine in cloud computing or serverless computing is actually what you need to perform microarchitectural attacks. So when it comes to setting up a serverless environment, like every cloud service provider that offers serverless computing does, in this case, you have to think about how to handle microarchitectural attacks. Otherwise, your customers, they could attack each other. And that is something a cloud service provider does not want, because tenants would not like this, right? Customers don't want to be attacked by other customers. Then in 2020, at the NSDI conference, there was a paper presented called Firecracker Lightweight Virtualization for Serverless Applications. And this proposes a lightweight virtual machine manager that can run many virtual machines on the same system, because it is so lightweight, it just doesn't use many of the resources. And you can start thousands of them on the same machine. And the thing is, they stated in their paper, for Firecracker, we provide clear guidance on current side channel mitigation best practices for deployments of Firecracker in production. So they took microarchitectural attacks in scope of their attacker model and said, we are able to handle them properly. And that was something we were not so sure about, because there are so many microarchitectural attacks out there. I'll just show you in a minute. So let's have a look at the background to fresh up your memory on everything we need for this talk today. First of all, virtual machines. They work like this. On the bottom, you have the CPU hardware, and then there's the kernel or operating system running on top of it. The operating system then provides a user land where you can run your applications. In the case of Firecracker, the virtual machine manager runs in user space and starts a virtual machine. The VMM on the right starts the virtual machine on the left. The green box around the virtual machine presents the virtualization barrier that is actually provided by the CPU hardware. So the hardware has support for virtualization. And if the virtual machine wants to use those virtualized hardware resources, it has to talk to the KVM, the kernel virtual machine manager or kernel virtual machine. And the KVM will then actually schedule the code on the CPU. If the virtual machine wants to talk to the outside world, for example, through Ethernet, so a network connection, or if it wants to store data on a block device, it has to talk to the virtual machine manager, and the virtual machine manager provides device emulation and I/O emulation to have the connectivity between the VM and the outside world. The VMM will then route all of this traffic through a rate limiting mechanism before forwarding it to the kernel that then will handle the I/O operations. And I've already explained the green color here, that is the virtualization barrier. And then we also have the blue color here, that is something Firecracker makes use of as well. It is the jailer barrier. The jailer makes use of operating system isolation mechanisms that limit the resources that are available to a virtual machine manager and the VM. For example, it can limit the amount of CPU cores being used by the virtual machine, or it can limit the area of the file system that is accessible, for example. Okay, so as you can see, this is a pretty typical virtual machine setup. The only difference here, or the special thing for Firecracker, is that the VMM is very lightweight, a very short or small code base that only supports a couple of well-defined devices and I/O emulations. So it is not fully fledged like QEMU, where you can just plug in any PCI device and it will work. But Firecracker is tailored to being lightweight and fast. So it only runs on Linux, and it only supports a couple of devices. Okay, and now we'll have a look at the MDS attacks and meltdown, so you have an idea of what those attacks are. Imagine this image as a timeline, so going from left to right, that's how the attack works. First, the victim has to access secret data. This could happen through a generic read or a generic write, but this could also happen through some cache eviction from the level 1 cache. So if the secret data is in the level 1 cache and it gets evicted, this would also count as a victim data source. Also, vector reads, or of course special register reads like the rd-rand instruction, they are possible sources of victim secret data. Whenever the victim performs such an operation, the secret data will be loaded into a buffer. For example, the cache, the store buffer, line fill buffer, store buffer, load port, or staging buffer. And depending on which buffer the data gets loaded into, the researchers that found the vulnerabilities gave the attack a different name. So yeah, if the data ends up in the cache, we call it a meltdown attack. If it ends up in the store buffer, we either call it fallout or riddle, depending on whether the data was loaded into the store buffer by a generic write or some vector read operation. We call it zombie load or riddle if the data is moved to the line fill buffer, and there is Medusa and riddle also reported for the load port. And last but not least, there's crosstalk that exploits the data when it's loaded to the staging buffer. Those are the red names I mentioned. Those are the names that the researchers gave them. And then Intel gave those attacks its own names that are more classifying what's going on. For example, we can see the MSBDS here for the store buffer. MSBDS stands for Microarchitectural Store Buffer Data Sampling, and MFBDS means Microarchitectural Fill Buffer Data Sampling. So as you can see, those names that Intel uses, they are more of a classifying nature, right? After the secret data is loaded into a buffer, the attacker can perform a generic read or a vector read, or also a of-core special register read to move the data into a register. And the special case here would be the of-core special register read, because this only moves the data to a different buffer, so the attacker then has to perform a generic read afterwards, for example. When this read or vector read happened, the secret data of the victim is present in a register of the attacker, and the attacker can now encode the secret data into a side channel to persist it before the speculative execution window ends, because it ends as soon as a fault occurs. So the problem here is that the generic read or the vector read was happening on some address, for example, that is not valid. So in this case, you would get a page fault. So the interesting thing is that the CPU forwards secret data of a victim to an attacker if some fault will happen later on. And what's interesting is if your system has TSX enabled, then you can even have more fine-grained control of how and when those faults happen. So having TSX on your system actually supports MDS attacks. This is why Intel disabled TSX on most systems through a microcode update. The main thing you have to take away here is that there are very many different MDS variants, and defending against all of them feels challenging already. On the other hand, we also have a look at Spectre attacks. Again, we have a timeline going from left to right that describes how such an attack happens. At first, the attacker has to train some prediction unit, like the pattern history table or the branch target buffer or the return stack buffer, that are all part of the branch prediction unit, or it has to mistrain the memory disambiguator. Then, after the mistraining, if the victim executes some code, certain instructions could be, or the outcome of certain instructions will be mispredicted because of the mistraining that the attacker performed. For example, conditional branches will be mispredicted if the pattern history table was mistrained, or indirect branches could be, or the target of indirect branches could be mispredicted. The return instruction could be, or the outcome of the return instruction, so the return address could be mispredicted. And we can also have store-to-load forwarding from one address to another that were predicted to be the same, but actually they were not. After the victim has a code that is executed because of some misprediction, some speculative window opens where this wrong computation continues. And during this computation, it might happen that the victim itself encodes secret data into a covert channel, like the cache and the S attacks or port contention. Those could all be possible covert channels, or those are possible covert channels that we have seen in the past in the context of Spectre attacks. And only after this happened, the victim code will realize that the transient execution was actually taking the wrong branch, for example, and then revert everything. But this is too late already because the secret data has been encoded into the covert channel. And all those different paths, they have different names. For example, there's Spectre-PHT, that is the name we give to the variant that mistrains the pattern history table. This is why we call it Spectre-PHT. And then there's Spectre-BTB, Spectre-RSB, and Spectre-STL from the same system, right? So BTB for the branch target buffer, RSB for the return stack buffer, and Spectre-STL for the store-to-load forwarding. Okay, that's it with the background. I hope your heads are not blown up, but you're still with me, because now we will have a look at the threat model that we were considering for our experiments. We considered two threat models. On the left, we see two virtual machines that run in user land, right? We have the green and the blue box, and the black box that is the virtual machine manager, the green box is the virtual machine. And we have two virtual machines from two different customers. On the left, we have an evil customer, some attacker customer. You can see this because of the devil's horns and the criminal hat. And on the right, we have a benign customer that does some secret computation. And the goal of the attacker on the left here is to extract information from what the victim is doing on the right virtual machine. And in the left case, we assume that those two virtual machines execute their code on the same CPU core in a time-sliced fashion. So only one virtual machine executes code at a time, and they interchange, right? And on the right, on the other hand, we say that the two virtual machines actually execute their code in parallel on two different logical cores of the same physical core. So on the right, we see a case where simultaneous multithreading or hyperthreading is enabled, and the attacker and the victim execute their code in two neighboring hyperthreads. And yeah, those at the top, you can see the two symbols that we will be using in the following to denote these two cases. So the pause icon on the right that describes physical collocation, and the white pause icon in the blue in the green circle, that is what we denote as time slicing. So what did we find? First, we had a look at the Medusa MDS attack, and we found two very interesting things. In the first column, you see the Medusa attacker variant, and in the second column, you can see the Medusa victim variant. And then we have two columns for the host system, because every experiment we performed between two VMs, we first performed on the host system to get some ground truth. And as you can see here, the cache indexing Medusa attacker combined with the block write victim, there was no leakage, right? That's why it says NA. So we did not see any leakage on the host system, and we assumed, okay, this attack will not work in Firecracker because the host system is not vulnerable in the first place. However, to our surprise, we found that this special attacker here, cache indexing attacker with a block write victim, actually the attacker is able to extract information about the victim in the case of time slicing and co-location. When the attacker and the victim run in separate virtual machines, the attacker was able to extract information from the victim. This only was stopped by enabling the MDS countermeasure on the host. enabling the MDS countermeasure in the guest kernel was not sufficient, and also it was not sufficient to disable SMT. So time slicing scenario was still leaking information from the victim to the attacker. And this is especially interesting for two reasons. First, the attack was not available on the host system, but we still see it in Firecracker. So it seems like Firecracker somehow enables this attack. We assume that this is because of the additional address translation that's going on. And second, the setup recommendations of Firecracker said that if you disable SMT, this is sufficient to be protected. And as you can see, this is not the case. And a second interesting thing that we found was the unaligned store Medusa variant with the rep move attacker, because here, again, the no SMT mitigation was insufficient. And to our surprise, also MDS was insufficient as a countermeasure. Only if we enable both countermeasures, MDS on the host and no SMT on the host, then we actually stop the attacker from observing leakage from the victim. Second, we had a look at the riddle attack. And here again, we found interesting things like in the case before, especially in the first row, you can see that if riddle leaks information through the line fill buffer in combination with an alignment fault, then no SMT is again insufficient to protect the victim from leaking its data to the attacker. So we have to enable the MDS countermeasure on the host. And as a guest, you can only check whether MDS is enabled on the guest system, but you have a hard time finding out whether MDS is actually disabled on the host. And you also have a hard time finding out whether SMT is enabled or not. So in this case, you have to trust the cloud service provider that they take the right steps to protect you from those MDS attacks. On the other hand, for 3 of the riddle variants, we found that no SMT is actually sufficient, right? So the L1DES attack and the riddle variants using the load port and the store buffer, they were well mitigated by disabling SMT. So the time slicing scenario did not show any leakage. So as you can see, most cases are handled well, but there are special cases that you have to take care of because you might easily miss them. Last but not least, we checked the Spectre attacks, and we found that Spectre-PHT still is a problem. Here I show you the cross-process variants that we tested. We also tested some in-process or same-process variants. You can have a look at the results on our paper. For the cross-process variants, we found that independent of whether we use the in-place or out-of-place variant of the attack, we saw leakage from the victim to the attacker. And that was independent whether we were looking at a time-sliced sharing scenario or a collocation scenario. On the other hand, we found that for Spectre-BTB, the no SMT countermeasure actually helps in the cross-Firecracker scenario, even though it didn't help on the host system. So the ground truth told us that disabling SMT will not solve the problem, but Firecracker actually manages to solve the problem in that case. The same is true for the BTB out-of-place variant. In this case, we didn't see any leakage when the proposed countermeasures were enabled. And also, Spectre RSB didn't show any leakage. So this is good news. And you might be wondering, where is the 4th Spectre variant that I was talking about earlier? Well, for the Spectre STL variant, there is no cross-process variant. So we cannot actually run it in 2 separate virtual machines, and therefore it doesn't pose any threat. Okay, let's conclude what we were looking at today. First, you might be wondering, what did you do with this knowledge? We first reported this to AWS, who is mainly developing Firecracker. And AWS updated their setup recommendations, and they also assured us that on their systems, everything we suggest to enable as a countermeasure is already enabled. And yeah, with this, I want to conclude. We found a Medusa variant that was enabled by Firecracker, even though it was not present on the host system. And there's also one Medusa variant that was not sufficiently protected when just following the setup recommendation that was the up-to-date version back then. Same goes for riddle. You have to take care that you enable all the countermeasures to actually make sure that you are protected. Spectre RSB and STL, they pose no threat to Firecracker VMs, because all the countermeasures that were recommended at the time of writing, they were sufficient. The same was true for Spectre-BTB. When you disable hyperthreading, then there was no leakage. However, Spectre-PHT still poses a threat because we saw leakage and we did not find a mitigation to stop the leakage. So Spectre-PHT still poses a threat today. Unfortunately, I can't be with you today, so if you have any questions, feel free to send us an email. Thank you.